So hello everyone, this is our project blockchain implementation with BLS signature aggregation. Now, what we basically did is that we took an existing blockchain implementation which implements a quite simple version of blockchain, and we added signature aggregation with BLS on top of it. Now, what is BLS signature? It's basically a signature scheme. It's a cryptographic signature scheme that verifies authenticity of a message. What it particularly allows us to do is that it allows signature aggregation, which means we can merge multiple signatures into a single one, and that one signature alone carries can verify all the individual messages. We can also merge all the public keys into one, and if there's a common message, it can be verified quite efficiently. Now, why should we use BLS? Well, the efficiency and the resulting scalability that it brings about with its reduced storage. So, thousands of signatures can be aggregated into a single one, and that is one of the things that make Ethereum proof of stake algorithm viable in the first place. Bitcoin also has an existing implementation of signature aggregation. It uses Nor signatures. Ethereum uses BLS. The main difference between these two is that Nor is much computationally faster, while BLS is more space saving. And here, for pedagogical reasons, we implemented BLS on our version of blockchain. We took help of the Stanford article. Let me show you. So this is the Stanford article that I have referenced here, and we implemented these four functions: generating keys, sign a message, verify a message, and signature aggregation. It required a group with bilinear pairing and a hash function. Now we used existing libraries for these two things and implemented all of this on top of it. So let me show you the code. So this is our bls.py file where we have implemented all of that. So we took help of this library to get a group with a bilinearing pairing function, and on top of it we implemented the keygen function, generates a pair of public and private keys, a sign function which can sign a message given the private key of the user, an aggregate verify function, aggregate sigma function, which aggregates all the signatures. So this six is an array of signatures, and this function generates an aggregated signature. This verify function, which can generate a single public key and a single signature given this message, and an aggregate verify function, which gets the aggregated signature, an array of public keys, and an array of corresponding messages. So let's say 10 users sign 10 different messages. And we have the aggregated signature, we have all the public keys and the messages that they signed. We can use this function to verify whether the signature is valid. So I wrote this test file where this is just a sample illustration of that. There are 5 messages signed by 5 users, and we get first of all an array of 5 pair of public and private keys, and generate a signature where the ith message is signed by the ith user, and we can supply in this aggregated sigma function with all the list of signatures to generate a single signature, and then we can use this to verify the aggregated signature. Now, the way that we have implemented this, first we have this wallet.py file and a miner.py file. This wallet.py file is basically the file from the perspective of the user, where the user can run their wallet. It basically has two utilities. First of all, generate public and private key pair for the user, and it writes down into these two files, and it uses the keygen function, and another which is the send transaction. So the user is asked in the second part of the code for to supply an address to send to and the amount that they want to send to, and this function is then called, which signs the message with the private key of the user with our BLS sign function, and then it sends all of that to the miner. The miner basically runs a server on their side, and in the server they can receive transactions. So when a miner receives from a user a specific transaction, we first of all call this verify validate signature function, which validates the signature using this verify function. And then if the signature holds true, then we add that transaction to our list of pending transactions. The miner, when it starts, it also generates their own public and private keys because when a miner mines a block, they need to include their reward for mining on these on the block, and so they also need to sign the block themselves. The miner basically perpetually runs a server function which can be used to receive uh, transaction from users, and a mine function which they continuously run to mine blocks. What it basically does is that it gets the list of pending transactions and call this generate aggregated block function, which first of all adds their own reward to the block. So this from network to the address of the miner with the signature that the miner themselves have signed with our BLS sign function. And then it gets all the blocks, all the transactions, pending transactions, and get their aggregated signature here. And then we return block with all these pending transactions where the pending transactions don't have the signature in them, but there's only this one aggregated signature that can be used to validate the block. Now let's see all of this in action. So I'll be running both of these wallet.py and miner.py file. So first of all, let me run the miner file. As we can see, it has started mining, and this is for a specific block. The data that it has is just a single transaction because there is no user submitting a transaction at this moment, and the block and the miner continuously add a transaction of their own with 1 unit of tokens from the network to their public key. This is the miner's public key, and there is only a single signature, this aggregated signature. Now, the miner will be perpetually mining all these blocks, but let's run our user file here. We can generate a new wallet. The keys are saved to the file, so these are here. So we have a public key and we have a private key. Both of them saved to the user's local file. If we run send coins to another wallet and enter the destination address. Now this address has to be a valid address, but let's, for our demo purposes, let's just write destination. The amount that we need to specify, let's just write a random number. Now first of all, we haven't implemented UTXO checking, so the miner won't be checking whether the user has this amount. We mainly focused on implementing our BLS aggregation, and we have sent this transaction to the miner, and they would have included it in a block. So here it is. So in this block, we have, this is a single block. This is that has two transactions. The first is the miner's own reward, which they are continuously signing, and the second is from the user that from the public key that we just generated. This is the public key that we just generated. Let's look on the start key, FCESJ, FCESJ. This is the public key that we just generated, and this amount, as we entered here, sent to destination. This has to be a valid address, but for demo purposes, we just mentioned destination. But as we can note, there is no signature for both of them. There is just a single aggregated signature. Now, how do we know that this aggregated signature is valid? Well, for that, in our code, next to generating this aggregated block, we have added this also assert for validate block. This assert basically checks whether the aggregated signature is valid. It gets all the public keys from the transactions and all the messages, and it calls this BLS aggregate verify function. Now, if the function is not true, then it will print there is a problem verifying signatures, and it will print the error, and it will return false. So assert will throw error, but we see no error here, and also there is no statement calling this printing this problem verifying signatures here. As we can see, the miner is still running here. So since the other did not throw an error, we can be sure that this BLS aggregate verify ran, and the aggregate signature is verified against both of their public keys. And that concludes our demo. Thank you.